A linked list is a collection of data structure connected by links that contain items. Each link is linked to another. Following arrays, linked lists are the most commonly used data structure. Through this course, we will learn about linked list, its applications and types. We will further understand the declaration, initialization, and implementation of linked list along with linked list demo and its advantage and disadvantages using the C programming languages. So stay tuned and learn all that you can about linked list using C. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions and I will respond to your comments.
Now let's talk about linked list. Let's understand what is linked list. It is a linear data structure. That means it is storing its elements, or the elements are stored in a linear fashion. Now, if the elements are stored in the linear fashion, that means all the elements can be stored as per the memory availability. Now, what happened in array, right? If we have this memory location, that means if we have a 16 bytes of size available in the memory, only then we can store 4 elements here. If the chunks of memory, right, there were let's suppose 8 bytes here and 8 bytes here, and we want to store these 16 bytes of memory or 16 bytes of elements. That means there are 4 elements in the array. We want to store those 4 elements in the array. We cannot, since elements can be stored as per the memory availability. That means in linked list we can use these chunks of memory, which was the problem in array, right? And that was resolved by linked list. That means we can use these chunks of memory. Now if your memory is available, that means if your memory is available in chunks, we can still use the memory efficiently. Now this is one thing, right? Now these two things are clear to you guys. Now the third thing is that you can access elements on a linear fashion, or you can access elements in a linear fashion only. That means if you have a linked list, let's suppose this is a linked list. We'll talk about this, why it is that I'm writing that. So now, in order to access this, you need to access all of these elements. Random access is not possible, right? So let's suppose if you want to directly go to this place, this node, it is not possible. You need to traverse all the nodes one by one. So in a linear fashion. So one by one you will go here, then you will go here, then you will go here, then finally you will go here and access this node. Now, like array, if you have this linked list which is of in which you are storing integer values, you can only store, that means the data stored in all the nodes will be of type integer. Okay, you cannot, there is no such scenario wherein if you want to store a float in this and int in this, that will not be the case. Okay, so you can only store homogeneous elements which is similar elements. So in arrays there was one more problem associated when we are using arrays. That means the size was fixed. So now in this, the size is dynamic. That means if you have 4 elements to be stored in a linked list, you can store them without wasting any memory or without having the condition where you cannot store more than 4 elements, right? So if you want to store 8 elements, you can store. Again, without wasting memory or without underutilizing your memory. Okay, or you can also let's suppose if I am saying in arrays the size was 4 and I want to store 8 elements, that was not possible. But here that the size is not fixed, it is dynamic in nature. Now we can easily insert and delete elements in the linked list. Now what you want to do, we want to insert an element in a linked list, right? We just need, let's suppose we want to insert a link node in here. So what we are going to do, we are going to just remove this link, add a node, link this node to this and link this node to this. That's it. So with the manipulation of single link, we were able to insert a node, which was not in the case of arrays. We need multiple swaps. Now, similarly, if you want to delete this element, right? So now let's suppose that we want to delete this node. Again, with the manipulation of single link. Earlier it was linking to this, now it's linking to this. That's it. With the manipulation of a single link, we were able to insert and delete a node, which was not in the case of arrays. We need multiple swaps. And also we need to keep this thing in mind while we are inserting, that there is a size available. Let's suppose if four elements are there already and you want to insert a fifth element, that means even if you're swapping it, the fourth element that is there, the last element will be lost. That should not happen. Okay. So again, now there's one more thing that is associated with linked list and which is very important, that the root node, that is this node, is the key, right? What do you mean by this thing? That this is the head of the linked list. That means if this head is lost, right, this is the pointer which is pointing to the first node, and this is the guy who is responsible or who makes it easy for us to traverse through the entire linked list. So we always keep the track of our head node, and it is generally termed, or root node is generally termed as the head node, right? And if head node is lost, your linked list will be lost. Okay. Now, if this head node is lost, your whole linked list will be lost. So you always keep track of this node. And even if you want to traverse, you always store this head in a temporary node and then change this temporary node, not this. It will always point to the first node of your linked list. Now let's talk about applications of linked list. So as we have already seen that if the memory chunks are available here and there, let's suppose 4 bytes are here, 4 bytes are here, 4 bytes are here. So we can use these in order to store 4 or 3 elements, right? And we can link them later on. So if you have a system wherein your memory is very limited, right? And you want to memory is limited and you want to use that memory to its full extent, right? It is suitable for those applications or the condition where your memory is very limited. So you can easily go for linked list. Also, we have seen that since there is not much manipulation required, right? When you're trying to delete or insert an element, let's suppose you are trying to insert a node, what you will do here? You will manipulate this link, you will link this to this, and this to this, right? And then what you're doing with the manipulation of a single link, you were able to insert the element. And same goes for deletion. If you want to delete it, you just have to manipulate this link and you are linking this node to, obviously in this case it is link, you are linking it to this node. So with the help of a manipulation of a single link, you are able to insert or delete the node. So it is the application which requires frequent insertion and deletion operations. It is also suitable for those applications. You can easily go for linked list because you know you will be saving a lot of time as compared to arrays. Now let's talk about types of linked list. So we have three types of linked list. We have a singly linked list, we have a doubly linked list, we have a circular linked list. Now let's talk about singly linked list first. So in singly linked list, there will be a pointer which is always pointing to the first node, right? That we have already seen. And that pointer is known as the head, or you can say the root of the linked list. And it is very important that you do not manipulate this head. If somehow you have manipulated this head, then you will get undesired results. Okay, so now this is how your node looks like. This node contains two parts, right? There are two parts associated with this node. One is the data part, another is the link part, or also known as the next. So this data contains the value, that is the homogeneous nature. That means if you're storing an integer value in this data part, you will always store data integer value in this data part. So this is what you store. Let's suppose you're storing 5 in it, right? So this is the data part. Now there will be some address associated with this singly linked list, right? Let's suppose it is 1000. Obviously, it will be hexadecimal number, but for simplicity, I'm taking this number as an integer. So now, and this address will be, or the reference will be stored by the root node, which is 1000. So this address is here. So now this link will always contain the address of the next node, that is this node. This will obviously have some address. Let's suppose this have 2000. So 2000 will be stored in this because this is pointing to this node. Okay. Similarly, this node will also have some data. Let's suppose it is 10, and it will be pointing to the next node, which is, let's suppose the address of this node is 3000. So 3000 will be here. And this will contain also some data, that let's suppose 15. And now since this node is not pointing to anything else, we'll store null in it. Okay, done. This is how your linked list, singly linked list looks like. So you have this data part and you have this address part. So these two parts will be always there when you're talking about a singly linked list node structure. Okay. So also this pointer that is pointing to the first node is the head pointer, and your last node will always contain next. In the next part, it will always contain null value. So this is how your singly linked list looks. Now let's talk about doubly linked list. If you talk about doubly linked list, there are two pointers or two things associated with it. So obviously this head node will always point to the first node that is there, right? This is the first node. And this will again be the key or the root of the linked list, or this time around doubly linked list. So this will store the previous address, and this will store the next address. So in this case, there is no previous address, so it will be null. And this will contain always the data part, which will be again homogeneous. So if you are storing integer, all of them will contain integer. So in this case, let's put a value in it, 20 and 30. Done. Now what happens after that? Let's suppose now this is its previous is null. What about its next? So it will have 1000 in it. Let's suppose the address of this is 2000 and the address of this node is 3000. Now again, just like we saw in singly linked list, this will always contain null. Okay, the previous part. So you have next part. So this next part will always contain null, and you have this previous part. You have this previous part. You have this next part. So let's first see how we can move in the forward direction. Now there was one drawback with singly linked list, that you can always move in a forward direction. So only one direction. You can move only in a single direction, that was in the forward direction. There is no way you can move in the backwards direction. So doubly linked list avoided, or mm, it rectified that problem with the help of this previous and next links. So previous links will always go help you to traverse in the backward direction, and obviously when you have this next in place, it will help you traverse in the forward direction. So now what happens this, or let's first talk about the next links. So obviously now this node is pointing to what, 2000. So 2000 will be stored in the next part. So again this will be storing 3000, and this will be storing finally the null values. Okay, done. But uh, what about the links which help us to move backwards? Those are previous. So it will point to the previous node, which is nothing but 2000. It will point to its previous node, which is nothing but 1000. It will point to its previous node, which is nothing but, in this case, it is null, because it is not pointing to anything else. So if we observe carefully, so there are two things that you should keep in mind, that the first node, its previous will always contain null, and the last node's next always contain null. So previous helps you in moving backwards, which was not possible in singly linked list, and next will always help you move forward, which was obviously the scenario in the singly linked list as well. Now let's move on to the circular linked list. So in circular linked list, again, this is the head node or the root node of the linked list. In this case, it is a circular linked list. So again, this node part will contain two things, the data and the link. So data will be, let's suppose data is 10, 20, and 30, right? Now this will have some, obviously some address. Now let's suppose these are the three addresses. Right? Obviously, these will be hexadecimal addresses, but yes, for simplicity, I'm taking this as an integer. So the link will contain the address of the next node, which is nothing but 3000, 2000 in this case, and 3000 in this case. But what happens in the circular linked list? Now, the last node, right, will point to the first node that is there. So the first node that is there is at location 3000. So you will store 1000 in it. Now you might be thinking, sir, this is similar to singly linked list, but the only thing that is different in this is that the last node in singly linked list was pointing to null, and in this case, the last node is pointing to the first node. Is that correct? Yes, absolutely. Okay. So the last node is pointing to the first node in circular linked list. But in terms of when you talk about singly linked list, at that time around, this will be null. In this case, in circular linked list, it will always point to the first node, and head will always point to this node, or it will always store the address that is 1000, and it will always point to the first node of the linked list, be it in any of the linked lists, be it circular, be it doubly. So again, it will store 1000, or be it singly linked list, it will store 1000. That is the first node. So with this, we are done with the types of linked list. So there are three types of linked list. One is a singly linked list, another is a doubly linked list, and the last is the circular linked list. So the only difference between singly and doubly is the last node, which points to the first node in the circular linked list. Now, in doubly linked list, it is similar to singly linked list. That means it has some features. That means we can move forward, but it has some extra features with which we can move backwards as well with the help of its previous part. And with the help of its next, we can move forward, which was in the case of singly linked list. And it was a new feature which was added to the doubly linked list, with the help of which we can traverse backwards. Now let's talk about declaration and initialization of linked list. So you might be hearing me say over and over again, the type of this is a node, right? This is a node, this is a node. Now how do you declare that node? We'll declare that with the help of this structure, and we name this as node. And inside the structure, we have two data members. One is of type data, or you can say the data part, and the another is the next, which is nothing but a self-referencing pointer which is pointing to itself, and obviously it contains the address of the next node. Obviously now it is contains the address of the next node, which is also of type node, so that is why it is a self-referencing pointer. So now here we have defined one. With the help of this temp, we are going to access the data members of this node. When you try to allocate memory, what are the things that you can use is the malloc function to allocate memory. And once you use this malloc function along with the size of operator, which is obviously of type structure, obviously you are calculating the size of this node, and then you are allocating that much amount of memory. And then finally, we are going to typecast it in to the type that is again of type node. Okay, and then we are given, or we get some address that will be stored in this in this tab. So this is how you will be creating your node, and in this case the data part will contain 1 and the next part will contain null, and the reference or the address that is there 1000 will be stored in this temp, because this is the temp which is pointing to this node. Okay, then so now similar to what we have seen, the data part and the next part, or the link part, right? This will contain the link, and this will be pointing to this node, this will be pointing to this node, this will be pointing to this node, and the last node at that point we will have, instead of this next, So instead of this address that is there, right? Obviously, it will have some address. Let's suppose it is having 4,000. This is 5,000. This is 6,000, right? And let's consider this to be 3,000. So now this 3,000 will be stored in this head, which is pointer, obviously of type node, and it is pointing to the first node of the linked list. Okay, this is pointing to the first node, and it will store 3,000, and this will store 5,000 because it is pointing to this. This will store 4,000 because 3,000 is pointing to 4,000, and this 5,000 will store 6,000. And now finally, when we are at the end of the list, this will store the null because it is not pointing to any node. Okay, so this is how you declare and initialize your node when you talk about singly linked list. Because again, this is a singly linked list because we only can move in the forward direction, and there is no way that the last node that is there is pointing to the first node, which is the case of circular linked list. And in doubly linked list, we can traverse backwards as well. So you might require one more self-referencing pointer that can be either previous, that can you can name it previous, okay? And this is the next. And in that case, what you will do, you will create another data member that is struct node, and it will create you will create a pointer and naming it previous, okay? So this way around you can create a singly linked list, and the structure that how it looks is like this. The two data members are there, and with the help of malloc you can allocate memory, and with the help of this arrow operator you can access the data part and store some value, and with the help of this next part you can access the next part and store some value in it. And this is the temporary variable. Obviously it should be tmp in this case. And TMP is nothing but a pointer which is pointing to the first node or any node in that case. Okay, so you will define it and you will initialize it. Now let's try to insert the element in the linked list and try to see the implementation of insertion at beginning. So here we have this function, right, which is known as insert underscore bit. So insert at beginning, and we are passing in the argument as the element that we want to store. Now let's suppose we are obviously in the main, we will be creating the root node, right? And we will be creating this globally so that we don't have to pass it to every function, okay? So now there will be two cases, right? Now since we are inserting at the beginning, right, there can be two cases. The first case is that our entire linked list is empty. And at that time, what will be the root that is represented here in this particular example or in this particular function is it is represented by p. So p will be null, right? And there will be a scenario wherein you have some nodes. It can be either one or two or three, it doesn't depend. Anything that is more than one will have to do a different thing, right? At that time we'll be having the address of this node, and then we'll be creating a new node in both of these cases, right? We'll be creating a new node, then this will act as the p node or head node, right? This will be pointing, this p or head will be pointing to the new node, and this will be now the new head, okay? So these are the two scenarios. Now let's see how we are implementing it. Now here we are just creating and allocating memory to the new node that we just created, right? And when we create this, we are creating a node wherein which in which this temp is pointing to this new node, right? And after that, what we are doing in this new node, we are pointing this temp's data to the element, right? We are initializing this data part, and we have the next part, right, in this new node, and we are initializing this data part with the element, right? Let's suppose this is 5. Now this is done, right? These two steps are done. Now we are checking if root, that is this p, which is obviously globally declared, right? So we don't have to pass it to every function that we create. Now if this p is null, right, that means our linked list is empty. Now let's suppose the first case is there, right? And at time what we are doing, we are making this temps next as null because there is only one element, right? There is only one node in the entire linked list. So its next will be null. And now what we are doing, we are updating this p because this is a globally declared this p, that is the root Now what we are doing, we are pointing this P to this new node, right? This is our root node now. And now, since it is globally declared, we don't have to even pass it. So that is why the return type of this function is void. Done. But this is one case. Now let's see. Let me just erase the unnecessary things that I don't want. Now, in this case, the next case, now we have this data part, or we have this node, we have this one node available for us. Now, next time around, when we are calling this function on, let's suppose 10, and we want to insert this 10 at the beginning. Now we have this time around, there will be some address allocated to this. Let's suppose this is 1000. Okay. Now we are creating a new node. Let's suppose we are creating a new node and it will have its data part and it will have its next part, right? Now 10 is stored in here and the next will be obviously will be dependent on certain factors, right? Let's not talk about next right now. And the data is executed. This is done. And obviously this will have some address. Let's talk about this address. It will be 500. Now, is our P equal to null? No, it is pointing to this node and it is 1000. So it is not null. So this won't be executed. Now we go into the else part. What we are doing, please go ahead and whatever is in the temps next, please store P in it. So P is pointing to 1000. So 500's next will be nothing but 1000. So this node is linked with this node. Okay. Now the next thing is we need to update this P. So in the last step after this else part is executed, P is pointing to this new temp. This is the temp, right? This will just be created. So this will be your P. That is your root or your head. Okay. Now we keep track of this head and this is not pointing to this anymore. Okay. So with this, we are always what we are always inserting our element at the beginning. So in both these cases, we saw what will happen. So the first case was wherein we will have our list is empty. That means there is no element in the linked list. And in the next case, we saw when our list is having some element, what will happen, or our list, there are some nodes available in our linked list. So this is what happens. Okay. So this is insertion at beginning. Now let's talk about insertion at the end, right? At the starting of when we talk about what is linked list, I talked about one thing that we will, we will never change our head. Never, no matter what. Because if that thing is changed, the whole linked list will be manipulated, or even in some cases, our list will be lost. Okay, so now what happens? We are trying to insert at the end. Now we know that in a linked list, we cannot access directly the state because we haven't kept track of this last node. So what we are going to do, we are going to traverse to this end and then insert the element, right? Now again, two cases are there. If our linked list is empty or if our linked list is having some nodes. Now let's clear this and let's see how to implement it. So we have this function insert end and we are passing in the element that we want to store. Okay. So now what we are doing, we are obviously if there are no elements, then this P will be null. If there are no nodes in this linked list, then P will be null. And what we are doing, we are storing that P because we don't want to change, because there will be some scenario wherein you have a single node here and this is 1000. So what we are doing, we are allocating or we are initializing this temporary node, temporary structure type of variable, right? Temp, and we are assigning this P to it. Okay. So this is also assigned to this node so that we don't change our head node, which is P. And obviously, again, these temp1 are defined globally so that we don't have to return it or pass it or even declare it. Okay. So now what happens? Now we are creating a new node that is tmp1, and we are allocating data to it. That means we are inserting the element that is 10 and we are always initializing it with its next part with null. Now why is that? Because it will be always inserted at the end. As we have seen earlier, what is the next of the last node? It is always null if we talk about singly linked list, not in a circular linked list wherein this will be storing the address of the first node, but since we are implementing this using singly linked list, so every time the last node next part of that will be null. Okay, done. So every time we will be creating a new node and its next part will be null. Done. So these are two steps. These two steps are done. And we have this temp pointing to this node. It can be either empty or you have some address. Okay. So now what happens? These two steps are done, right? Now we check if P is null. That means if this is the scenario, at that time, what happens? We'll point this P to this TTMP1. That's it. We are pointing this, and this will be the last node. Obviously, if there is no node in the linked list, that will be the last node of the linked list, okay, because there is only one node, right? That will be the first node, that will be the last node. None, but and this part will not be executed, and we are done with our process. But what happens if there is a node? Now let's talk about this scenario, right? Let's suppose in the first case we didn't have anything, and in the next case we had this. Okay, so this is our data part, and this time around we are trying to solve 20. So what we are doing, we are pointing this TMP so that we don't change this, because this is very important. We never change our root node. We have this temporary variable which is pointing to this node, right? And this is of structure, right? This is of the same structure that the every node is, right? Now we created TTMP1, and in that TTMP1 we are storing what, 20, and in the next part we are storing null, because obviously it will be stored at the, it will be added always. We are inserting an element, inserting a node at the end. The next part is null. The data part is 20, and obviously this will have some address. Obviously this will also have some address. So 2000, and this is 1000. This is 1000, this is 2000, and this is TTMP1. Done. So these three, four steps are done. Now is p equal to null? No, in this case we're pointing to 1000, so this will not be executed. Let me go into the else part. Now what we are doing, we will traverse to the end. In this case, there is only one node. So what will happen? We'll check if temps next. What is temps next? It is null. It should not be null. Unless and until it is not null, we'll traverse. So we are not traversing. So now what we are doing, in this case, this while loop will not be executed. Okay. So this will not be executed. So what we are doing, we have this temp pointing to the same, right? This TMP is pointing to this, because this while loop will not be executed. And then what is the next step that we're doing is temps next, please put temp1. That means this temp1, which is ttmp1. Let me just erase it over here. This is 2000. Please put 2000 in temps next. Temps next is null. Please put 2000. So it's successfully added this new node at the end. Now let me just quickly go ahead and reiterate what I just said, but this time around we have two nodes, okay, so that we see this iteration happening, we see this loop working, okay. Just a minute, let me just quickly clear it. So now let's suppose we have this P, and in this P we have 10, and this is 2000, okay, this is 1000, and this is 2000, and 20 is there, and this is, okay. So now let's see what happens. This time around, insert and is called, and we are passing in 30. Done. We have this temp which is pointing to this because we don't want to change it. This is TMP. We created a new node with, and it is TTMP1, and obviously this will have some address. Let's suppose it is 3000. Its data part is, and it's having next part. Its data part is 30. That is passed, and its next is null. Okay, because we are adding it at the end. So these four steps are done, right? We check if P is null. Is P null? No, it's 1000, because this P is nothing but our head node. Okay, you can also represent it by head. Okay, now if you're not comfortable with P, so this will not be executed. Now what happens over here? We'll check if we will check the condition, and we will loop around so that we are at the end. So we check, is temps next null? Is this temps next null? No, it is not. So what? Please put temps next in temp. So temps next is 2000. So this will be pointing to this now. Okay. So this is gone. What happens after that? Is temps next null? Yes, it is null. So we will be out of this loop. And then what happens? Please put temp1 in temp1 in temps next. So temps next is null. Temp1 is 3000. So we are putting 3000 in it. So there will be a link. That means this is pointing to this now. So this is how you insert your node always at the end. Now, what will be the time complexity in this case? Now, since we are executing, in the worst case, we will be executing this in such a way that we are always traversing to the end of the list and storing that element or inserting that element. So the time complexity will be bigger of n. Now, if we talk about this case, wherein we were storing at the beginning, right? Always storing at the beginning. In this case, the time complexity will be what? Constant. We are always storing at the beginning. Now we don't have to traverse anywhere, right? So that is why the time complexity in this case will be big of when. In the worst case or in the best case, right? It will be always big of 1. So now let's talk about the implementation, and we will trying to delete, or we will try to delete the beginning, or we'll try to delete a node from the beginning, and we'll try to do it always. Now again, since we are deleting, so we will not be creating, so malloc function is out of the picture. So now we're deleting. So again, there will be two scenarios. What the first scenario is that obviously the ground rule is saying that p will never change. That means your head node will never change. So the first thing is that if you don't have anything in, that means there are no elements in the linked list. So if your p is null, or if your p is having some errors, that is if you are having some nodes, so can be 1,000, can be two nodes, one nodes, can be anything. Okay. So now let's talk about these scenarios one by one. So in the first case, right, let's talk about this. So if your p is null, at that time around you cannot delete anything, so you're printing a message no element can be deleted or no element to be deleted. Done. That's it. Now what if you have a single node, or if you have two nodes available? Okay, now let's suppose this is 10, this is 20, and this is 2000, and this is null, this is 1000, this is 2000. Okay. So P is here, obviously the root node, or the head of the linked list, right? So we are checking. Obviously, we keep track of. We are not going to change our head node every time we are deleting from the beginning. We are changing our head node, so we need to keep track of things, right? So we have this temp pointing to the first node. Now, is P null? No, it is not. What will happen in the else part? We go and print out the data part of this, that is of this. So 10 will be printed because we are going to delete this. So we are just printing out the message, okay, this is the element that is going to be deleted. And then what we are going to do, please store P's next in P. So P's next is 2000. So we are going to store it in P. So that means this P is now pointing to this. Done. That's it. That's how you delete. Or if you want to be even, if you want to add one more step, you can do what? Please, now you have this P pointing to this. In the next step, what you can do, you can just update this so that this link is not here. So what you will do, please add, or please put temps next, whatever is in the temps next, which is 2000. Please go ahead and put null in it. So this will be null, and so this link is broken. So then we can just free this. Okay, that's it. So now this is how you delete the node from the beginning. Now, if you talk about time complexity, it will be always, since we are always deleting at the beginning, so we will always have the head node that is pointing to the beginning. So we don't have to traverse anything. So again, it will be of order that is constant amount of time. That is big of 1 in worst case. Okay. Now let's talk about the same, but this time around we will be deleting our element at the end. Okay, so we will be deleting always, we will traverse and we will delete at the end. So it is quite evident from now that obviously we will have to traverse, so the time complexity will be big off and in the worst case. Okay, so that is out of the picture. So now how will we delete at the end? So obviously there will be these two scenarios. What? First, that our linked list is empty, and the second, there are some nodes so that we need to traverse and delete the last node. Okay. So now what happens if the linked list is null? That we will just say, okay, there are no elements and we are done. So this will be executed. This else if will not be executed, and this else if will not be executed. Done. But what happens if there are three scenarios in this case when you're deleting. So the next case is if there is only one node. Okay, so this is done, right? But what if there is only one node? That means P is pointing to this node and P's next is null. We'll check. Okay, if P's next is null, at that time around, print this data and put P to null. So that we can just directly go ahead and put P to null. That means there was one element and we removed it. And now P is equal to null. And we are back to this scenario wherein P is null. So these are two scenarios. Okay. Now let's talk about third scenario. And both in these two cases, the time complexity will be constant because we are not traversing anything. But we always keep when we talk about time complexity, we always talk about what the worst case. Okay. So in the worst case, we need to traverse. Let's suppose we are traversing to the end, and in that case, it will be big of n. Okay. So now let's erase everything. So these two cases are clear to you. Now let's talk about the final case, right? So what we are doing, we have, let's suppose we have these four nodes and let's suppose this is 100, these are addresses, okay? 200, 300, 400, and this is null. Okay, let's suppose this is 10, 20, 30, and 40. So this is 200, this is 300, and this is 400. And this will be your P. Okay, so these two conditions or these two blocks will not be executed. Now, what we are doing, we have this temp. Obviously, this will be happening in all the three cases. So temp is pointing to this, and we are creating a new variable that is known as pre. Okay, obviously it is of type structure of type node. Okay, so this is another pointer that we have over here, pre, and this is right now this is null. Okay, none. So what we are doing now, we have this temp in place. Now what we are doing, we are going to traverse, we are going to check. Okay, now what is happening, now this temp we will check. Okay, now we will just traverse first with the help of this while loop. We'll check, is temp's next null, is temp's next null, no, it is 200. Then what we are going to do, we are going to keep track of this node as well as we are going to move this pointer to this position. So now pre will contain temp. So temp was pointing to 100, so pre will contain 100 and temp will point to this. Done. Again, is temp's next null? No, it is 300. Keep track of temp. Temp is pointing to 200. 200 is there. So this pre will point to this. We have the previous node, and the next that is there is this temp. It will be pointing to this node now. Okay. So this link is gone. So now this way we have this temp over here. Next time, is temp's next null? No, it is 400. Okay, then what you're going to do, please put pre to this node. So this will be pre, and now our temp will be here. Temp is here. Okay, done. So let me just clear out everything else. So finally, when we are at this position, so pre is here, temp is here. Let's remove the rest of the things. Again, keep this thing in mind. We're not changing the p, that is our head node. So now this is our pre and this is our temp. Now once again, is temp's next null? Yes, it is null. We are out of this for loop. Now what we are going to do, please put pre's next to null. Okay, this is just to keep track of that node so that of the previous node so that we can just remove this node directly by just updating the previous next. So previous next was 400. Please put null in it. So this link is done. This link is gone. This link is manipulated. So we don't have this node anymore. We cannot access this node. And after that, what we are doing, we are just printing temps data, which is 40. So we are just printing 40. So this is how you delete your node in the linked list, and we're deleting it always at the end. Okay, so previous and temporary. Can you either you can use temp or you can use two pointers like previous and next. So previous will be this and next will be this. Okay, so you can put relevant names as long as you're comfortable with those names. Okay, instead of p you can also use what head. Now, let's talk about how to display the elements or how to display the data present in the linked list. Let's suppose this is your linked list. Okay, so this will contain 10, this is 20, this is 30, this is 40, and obviously this will have some address that is 100, 200, 300, 400. Okay, this P will be pointing to this. Okay, and this is obviously a head node, so this will contain 200, this is 300, this is 400, and this is finally null. So now, in order to display elements or display the data present in our nodes, what we are doing, we have this temporary pointer which is also pointing to the first node, so that we are not changing this head node. Then we'll check, is temp equal to null? No, it is not. It is pointing to this node, that is 100. So it is not null. What we are going to do, we are going to print temps data. So we are printing 10, and then we are updating the temp. So we are updating it. So this will be pointing to this, because we are going, what we are doing, please put temps next in temp. So temps next is 200. So this will be pointing to this now. Okay. Again, is temp null? No, it is not. 20 will be printed. It will update this. We'll go to here. Is temps next null? No, it is not. It is 400, right? So please print temps data, which is 30. Now again, is temps next? Again, we are updating it. Is temps next null? No, first we are going to see, we are present here, then 30 is printed. Okay. So now what we are doing, is temp null? No, temp is pointing to this, right? 400. We're not checking temps next, we are checking temp. Okay. So is temp null? No, it is 400. Print temps data, which is 40. Please update temp to temp temps next. So temp will be pointing to now null. Is temp null? Yes, it is. Out of this while loop, done. We have printed all the elements. Now again, if you talk about the time complexity over here, since we are traversing all the elements in the, or all the nodes, the time complexity will be big off and right in the worst case. Now that we have covered all the implementations, now let's go ahead and implement this in code blocks. Now what is happening? We are including these libraries that we require. Okay, so then we are defining a structure that is of type node. Obviously, it will have data part and it will have the next part. Then we are declaring these global pointers or global variables of type node. Okay, so that we don't have to pass it to every function that we have. Okay, so we have a function over here that is void insert at end. That means the return type is null. Return type is void insert at beginning, delete at what at the end, and then finally we have display function. Okay, so these are some methods. Okay, so now what happens over here, we have this main method, and in this main method we have an integer that is val and n. So now this is a value that we are going to insert, right? The data part, what we are going to, then we have this root node or the head, which is equal to null. Okay, now we are creating a menu kind of a thing, so that we keep track of what we want to do. So you're here, if you see, if you press 1, we are going to insert at the end. If you're going to print 2, we are going to insert. If you're going to press 2, we are going to insert at beginning. That if you press 4, we are going to delete from beginning, we are going to delete from end, then we are going to press, if we are pressing 6, we are going to display all the elements, and 7 from exiting or from the program. Okay, done. So this is a menu. We are going to use a do while loop. So then we are going to scanf. That means then we are going to press okay, ask the user, okay, enter your choice. Do you want to insert at beginning? Do you want to insert at end, delete beginning? And now what is your homework? Try to implement insertion at any position depending upon the location, right? Let's suppose there are 5 nodes. I want to delete the third node. Try to implement that on your own. Okay, that's a little homework for you guys. So enter your choice. You just press 2. Okay, scanf does your end will have now 2. Then what we were doing, we are using a switch case. Okay, if the user is entering 1, that means enter the value, and then we are going to enter the value, and then we are going to call insert at end. So 1 is for inserting at the end. That is case 1. Case 2, if you're pressing 2, that means you're inserting, you want to insert the element that you just entered, the val. That is why we have these 2 pointers over here, the val and n. Okay, for inserting the value. Okay, one is the choice and another is the value. So we are going to call insert at beginning. If you press 4, we are going to delete from beginning. If you press 5, we are going to delete from end. Obviously, now since you are using switch case, we don't want to execute all these function calls. So we are having break, so that we are out of this case, and so that we are not executing the rest of the cases. Okay, so now we have, then finally we have this case 6, which is to break, right, which is to display all the elements, and then 7 to exit from this program. And finally we are not pressing any of these 1 2 4 5 6 7, any of these. We are going to print wrong choice, and then we are going to break, right? And Also, we are going to wait if you want to continue or not. Let's suppose I told you, okay, do you want to continue with this process of entering values or deleting values from the linked list? I'm going to wait unless and until you press Y. That is, you are pressing the character Y, we are going to continue. Unless and until you are pressing anything else apart from Y, that is in the lowercase y, that is, you see, Y, whatever you are pressing, that is for which we are using this get function, okay? GTCH, get character, okay, function, okay. So this is our menu, and we have already seen these implementations. We are inserting at the end, we'll traverse to the end and delete in one case. And if there is no node at that time we are deleting, we will print a message. Or this is not for the delete, okay, this is for inserting at the end. So again, we are inserting at the end. We will, if you don't have any linked list, if you don't have any node in the linked list, that will be our new node, and that will be the element or the node which is at the end if there is no node. But if there are nodes, we are going to traverse and insert the value or insert the node there. Now, if you talk about insert at beginning, obviously there will be two scenarios. You can put it in that way, which I just showed you in the implementation, or you can just put it in this way. This is much more efficient as compared to that. Okay, so simply there will be two scenarios. In that case, what we did, we have p to null, or we have, that means there are no elements, so we'll insert the element at the beginning. And in the next, what we are going to travel, we are going to insert at the beginning, so we are just going to update our root node in that case. So this is what we are doing, we are updating our root node at the end. Okay, just scroll through it, do it right, you will get the intuition what I'm doing. So basically what I'm doing, I'm creating a new node. Okay, I'm checking if temps data, okay, this new node, I'm inserting the values. What values? Whatever is the data part, that element I passed, as to I inserted it in the data part, and whatever is in the temps next, I'm going to store p. So p can be null in one case, right, wherein there are no elements at that time. The temps next will be null, done. And then we will update our p to temp. That will be one scenario wherein we don't have any elements, so p will be pointing to the first node. Now what if we have our node available? What at that case, what we doing, we are having this temp one, that is our new node. We update our data part, we update our next part with p, because now this will be our, the p will be pointing to what, the head, earlier head. Now that will be temps next, so the link is there. Now we need to update p, so p is temp one. That's it. So this does the same thing that we did in that case. Okay, therein we were explicitly defining two cases. Here we are smartly doing this. Okay, you just try to implement it. Okay, then this is insert at beginning. Now delete at beginning. So there will be two cases. If we have null, then no element is deleted. If you don't have, then we print the data, and since it is beginning, then we update our p. So p is next. Done. If you want to, if you want to delete at the end, so what we are going to do, there will be again two scenarios. If p is null, that is if head node, there is no head, right? At that time, what you will do, you'll just say, okay, no elements are found, and there are no elements that you can delete. And the next scenario, what we are going to do, you're going to see, okay, if there is only one node, right, there will be three scenarios in this case. The first, if there are no elements, if there's a one node, if there are multiple nodes. If there's a one node, you are going to update your next to null, and then print the data and initialize your p to null, because now there are no nodes. Okay, and the third case, you will be just traversing to the end and then deleting that, and also printing the data part. Okay, so let's minimize this as well. So finally we have this display method, wherein we are just using this temp to traverse through all the nodes that are present in the linked list, and printing out data one by one, and updating our temp to temps next. Okay, these are, let's just minimize this as well, and let's just minimize this as well. So you have 1, 2, 3, 4, 5 functions, and you have your menu in place. Now let's try to run this. So let's do a build and run. So now you have your menu in place. So now let's try to enter your choice. Let's suppose we are trying to insert at beginning. So you will press 2 and then press enter. Now you enter a value. Let's suppose we are entering 50. Okay, you press enter. Do you want to continue? Apart from Y, you will not be able to continue. If you press Y, that means yes, you want to continue. Okay, so now if you just, let's suppose if you press a wrong choice, let's suppose you are pressing 8, at that time it will say wrong choice. Do you want to continue? Yes, we want to continue. Okay, so now let's suppose we are going to insert again at beginning. So you press 2, Okay, do you want to press? Okay, so he said, do you want to continue? So we were only having one choice. That means whenever we press Y. So I pressed 2, so it break out of the program and our program was done. So now let's try to run this thing again and see different things. Okay, okay. So now let's press 2 and let's insert a value. Let's suppose we have 40. Do you want to continue? Yes, press a Y. Okay, enter your choice again. So we will press again 2. We are again going to insert at the beginning. Okay, then let's enter value. So this time around, earlier we entered 40. Now this time around we're going to enter 30. Press enter. Do you want to continue? Yes. Again press 2 for inserting a value at the beginning, right? Enter your value. We are going to enter 20. Okay, now press enter. Do you want to continue? Yes. Again we are going to insert at beginning. We are going to insert. We press 2. Again we are going to enter a value, that is 10. Now do you want to continue? Yes. So now if you observe carefully, I inserted 40, 30, 20 and 10, but all of them will inserted at the beginning. So if you want to traverse through them and you want to print the whole linked list, what should be the output? It should be 10, 20, 30, 40, right? So now let's try to display all the elements. Let's press 6. So it is 10, 30, 10, 20, 30, 40. Okay. Do you want to continue? Yes. Now let's try to delete from the end. So we are going to delete from the end. So which element will be deleted? It will be 40. So now let's press 5. So now, okay, 40 is the element that is deleted. Do you want to check if that element is deleted? Yes, we want to continue and we will display it again with the help of 6. And again, now this time around it is 10, 20, 30. Now let's try to delete from beginning. The 10 will be deleted, so that 10 is deleted. We'll also check if that function is working correctly or not. So delete from beginning, it is 4. Okay, we entered the wrong choice. Okay, we needed to enter yes. So you get the point, right? So all we need to, he said, do you want to continue? So I pressed 4. That is not the input, right? So the input should have been Y. It was expecting. So now since we entered the wrong character, so it break out of the program. Okay. So this is the whole implementation of your linked list. So this way, in this way, what we just saw, right? Let me just clear my screen. So in this way, we just saw 5 functions, right? Insert at beginning, insert at end. We also saw delete from beginning and delete from end. And we also have this display function wherein we are just displaying through the elements. We also saw the implementation where we built a menu. In that menu we inserted all these functions, and one by one we were implementing that with the help of get character, and we were just building kind of a menu and then then calling these functions one by one. Now you can also implement this insert at beginning and end in a single function that is known as insert at anywhere, right? So depending upon the position, you can insert either at the beginning or the end or anywhere in the middle. Same goes for this. You can delete anywhere. There's a function you can try to implement it on your own. Okay. Now let's talk about the advantages and disadvantages of linked list. First, let's talk about the advantages. So obviously, as compared to array, right? When we talked about arrays, they were fixed in size, right? We need to specify the size in the subscript. So fixed in size, which is not in the case of arrays. It is dynamic in nature and you can add as many nodes as you want depending upon your requirement, right? So obviously when you have that uh, independency over the size, you will never, there's no chance of wasting any memory, right? So if you require 4 nodes, you will use 4 nodes. If you require 3 nodes, you will add 3 nodes only. So in this way, the size of the linked list is entirely dependent upon your application. What are the things that you require, you make them, that's it. So you will not be wasting your memory and you will be utilizing your memory very efficiently. So this is the reason why this is written over here, the efficient memory allocation. How you are doing efficient memory allocation? Let's suppose you have chunks of memory available here and there. You can link them together and allocate the memory and use those memory location for storing the data, right? So and it is very easy to insert and delete node in a linked list just by manipulating a single link, as we have seen earlier. Just if you want to delete this, you just manipulate this link and just point this link to the next node, which is after this node. That's it, you are done with the deletion operation just by manipulating a single link. Similarly, when you're talking about insertion, at that point, you just you if you want to insert at this location, you remove this link, point it to this, and then remove and point this new node to this node that is there, that was already there. Again, we are manipulating a single link. Okay, just the manipulation of single link here, that is required for insertion, and a single link here, that is required for deletion. Now when we talk about disadvantages, one of the major disadvantage is that you cannot lose your head, right? The head node that is pointing always to the first node, either in a singly linked list or a doubly linked list or a circular linked list. This head node cannot be lost. If this head node is lost, or if it is manipulated, right? If the head node is lost or manipulated, the whole linked list will be lost, right? Let's suppose this is your linked list, and somehow, right, if this is the head node and somehow you made it traverse to this particular point. Right now head node is pointing to this in a singly linked list. Now there is no way you can access these nodes, and you will get undesired results. Another disadvantage is that you cannot access randomly. So random access is not possible, because if you want to go at this particular node, you have to traverse through the first three nodes first. Why? Because this node knows the address of this node, this node knows the address of this node, this node knows the address of this node. There is no way you can directly go to this particular node. Random access, that was there in the arrays. With the help of indexing, you can randomly access the elements. That is not possible in terms of linked list. And the address of the first node is known to the head of the linked list or the root of the linked list. Okay, so that head is pointing to this first node. Okay, so you cannot change or manipulate or lose, or you cannot lose your head, because the whole linked list will be lost. Okay, and the random access is not possible in linked list.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.